Okay. Right.
So I can cover it with the...
So we continue this morning, but before we start, again, to the speakers, please send Maxime Leroy at CE.fr your slides. Maxime says no keynote. You know, I'm a keynote user, so, but it's better for him if you convert it to PDF. But please send it to at least 24 hours. Sorry? Oh, PowerPoint, but nobody uses PowerPoint. Okay. Anyway, continuing this morning, sort of. Yep. Ah. He wants to use an iPad. If you have any questions, you see me at lunch. The short answer is we can cope with anything. It just drives him crazy, and that's fine. You know. Anyway, fantastic. So once continuing this morning, the next speaker I'd like to have is Gregorio Carullo, and his title: Gravitational Wave Signatures of Beyond Kerr Observational Status, Developments and Perspectives. Thank you very much.
Thank you. Yeah, I think I was the first one to drive in crazy with the keynote, so sorry about that. All right, so we tested the room. I assume this is working.
Okay. Should be, yeah.
Perfect. Okay. Yeah, thank you very much for the invitation, of course. I'm a bit of an outsider from this community. You might have noticed because probably nobody knows me. That's because I work mostly on gravitational wave observations, and I have a foot in modeling, but I mostly work on data analysis. But yeah, last year at Galileo Galilei Institute in Florence, I met Josif and Daniel and many other people. And for me, starting to think about more exotic compact objects which also have a motivation from fundamental physics principles has actually been a very interesting and useful learning experience. All right. So just to give you a general flavor of what I'm going to cover in the talk. So I try to focus on, so we do a lot of tests, what we call tests of general relativity. So we search for beyond GR signatures in many different ways. Every time the LIGO and Virgo collaboration put out a catalog, there is a companion paper, which is called the Testing GR paper, where we put all these tests together, including some that Daniel mentioned. And I try to select the results, which I think and I hope will be most interesting for this community. And other than that, I'm going to focus on some work with collaborators where we try to think about fundamental physics implications of these signals. Okay, so the outline is we'll discuss signatures of beyond Kerr from black hole coalescences. And then I'm going to focus on the topic I'm mostly expert on, which is observational black hole spectroscopy. And then I'm going to discuss fundamental physics implications from gravitational waves observation. So what can we learn about new fields or new length scales in nature? And then the last part of the talk hopefully will be more connected to what's being discussed here, which is we observe quasi-normal modes and we observe these signals, but what can we say about the horizons? Because that's what we actually care about. And finally, I will discuss briefly the prospects of measurements with future gravitational wave detectors. Okay, so what have we observed? Typically, we observe these signals. So we observe a time-dependent strain on interferometers, and we can feed them with templates of binary black hole coalescences. So in time and frequency, this looks like a blip. It's a characteristic chirp signatures, and somewhere here there is the Ringdown. So now we have multiple detectors online. This is a detection with 2 LIGOs and 1 Virgo, so 2 in the US and 1 in Italy. And once you get these data streams, and once you start to analyze them, you interpret them as coalescences of black holes. So maybe this is a bit dark on the projector, but basically I'm just projecting all. So the Y scale is the total mass of these black holes. And in yellow, you have the neutron stars observed in electromagnetic waves. In red, the black holes observed in X-rays. And then in blue, you have the detections from LIGO, Virgo, and Cagra. This was in 2019, so after the first observing run. And you see that we still got a good number of detections, but black holes were mostly observed in electromagnetic waves. Then in 2020, we got this. And in 2021, we got this. And now the detectors are online. So you can see that in a few years, we passed through 5 events to 100 events. And there's a lot of features. So they're ordered in no particular order, but there are a lot of features here. For example, people were wondering about a mass gap between neutron stars and black hole. And if there are objects which can fill this mass gap. We already have one. We have a detection. It's a strong detection of an object which has a total mass, a secondary mass of 2.6 solar masses. So there is an object. We don't know if it's either the heaviest neutron star ever observed, or the lightest black hole ever observed, or something else. It's this guy here. So it's a very tiny thing that merges with a 20 solar mass black hole to form a heavier one. So there are a lot of features in these diagrams. Yeah, you can see binary neutron stars, and black holes. We observed a lot of variety of objects, and some of them are puzzling. We have no clue about what this guy is. Whatever it is challenging all the formation scenarios, black hole formation scenarios, or the neutron star equational state scenarios. So yeah.
Why is it challenging? 2.6 is perfectly fine for a black hole. So
yeah, but the point is we have never seen a black hole which is this light, and it's not trivial to decide if it's a black hole or a neutron star. Actually, we don't know. Yeah, it's not a subsolar mass thing that would be actually a breakthrough, but still. Okay, so of all these 90 events, only 50 are good enough to start doing precision physics, so searches for new physics, and especially the top ones, which are the heavier ones, are the ones where we actually can use where we can see ring-down signatures, because we need heavy black holes to give us good, confident enough detections. This just depends on the bandwidth of the detectors. Okay, and actually, yeah.
What is the x-axis?
They're just ordered to make it nice, a nice graphical thing. But it's all so. Each vertical line is a detection of either a black hole or gravitation, or in gravitational waves. Yeah, yeah, it's a Rorschach test. Whatever you see. Okay, but the good news is that since a week ago, the detectors are now online again for a new observing run, and they are more sensitive than ever. And this, of course, these cycles of improvement is going to continue at least for another few years. Okay, so what do we want to learn from these signals, or what do we hope to learn from these signals? So first of all, we want to test the emission, and the kind of questions where we are interested in asking is, are we really observing black holes? So what are these things? They are dark compact objects, that's for sure. But are they black holes? And if they are black holes, or if there are something which looks like a black hole, is GR actually a correct description of the dynamics of these objects? And do they have possibly additional hairs? And then you can start to go crazy and think about quantum horizon effects. And so the idea is our classical descriptions of black holes valid or not? So as Daniel discussed, and I'm sure you all know by now, that these coalescences take place in 3 phases. There is an in-spiral phase, where essentially it's a quasi-adiabatic evolution. You have post-Newtonian theory, plus you need some resummation techniques, and this is all nice and fine. One interesting thing that we can learn from this phase where the two objects orbit around each other, for example, is looking at the spin-induced quadrupole moment. So you know that if the black hole is spinning, the spin will give it a quadrupole moment, and it's something that for black holes, you have a constant here, k. So chi is the spin of the dimensional spin of the black hole, then there is the mass, and k is a constant, which for black holes is 1. For neutron star is somewhere between 2 and 14, and for boson stars, for example, is between 10 and 150. So if we measure something which is, a k of 30, then it's not a black hole and not a neutron star. We have measured this. Actually, what we measured is the symmetric combination of the k's of the two objects that are spiraling, because the post-Newtonian phase is sensitive to this parameter. And so here is the deviation from the k predicted by GR. So there are 2 measurements. One measurement where we assume that these k's are the same for the 2 objects, and one when we don't assume that. So you see that 0, which is the GR predictions, falls well within the distribution. So for now, there's nothing there. But you notice that it's very skewed towards negative values. That's a funny feature, but it just because of the correlations with the spin. So you see that the spin enters here directly. So what this is saying actually is that most of the black holes we are seeing, they are spinning up in the positive direction. And so you have a counter effect here. But these start to be interesting. It's like a 2 sigma tension or whatever. Okay, this is an interesting feature which could connect in principle with other dark compact objects. Of course, to do a proper model of this, you would need to include higher modes, you would include tidal polarizability, tidal heating, which I'm going to discuss a bit more later. So this is not a complete model. It's just a model where you take one piece that you know in Kerr and you try to go away from it. But it is not a consistent beyond Kerr model. Then there is the second phase, which is the most dynamical one.
What is the I and M?
Yeah, so chi is the dimensional spin of the black hole. M is the mass.
And kappa is what you're measuring?
We are measuring, well, we are putting a deviation on this kappa. So actually we are putting a deviation on the sum of this kappa, so some delta k parameter, and we are measuring if it deviates from 0. So when we fit the whole waveform, we allow for a deviation here, and we measure that.
So suppose there was a consistent bias away from them, but having both the same kappa, would it create that kind of shift?
So sorry, can you say?
So suppose that all the black holes you looked at, one of them had a kappa of 3 halves the average value, and the other one had a kappa of half the average value. Would it create a bias like that?
Yeah. So the bias, this bias would so for now it's consistent just with statistical errors and the fact that the black holes have positive spin. It's just a correlation with the spin that's creating this for them. Yeah. If it start to if this line goes to the very large tail of the distribution, then it's not. So the GR prediction is kappa equal 1 for a black hole.
Okay, so you're just the measured kappa minus 1 is what you're plotting.
Something like that, yes. Okay, the second phase is the plunge merger phase, which is a highly dynamical thing. And for now, it can only be fully described using numerical relativity. Here it is NR. So these, of course, it's highly dynamical. It's very difficult to describe analytically. The best, so I'm trying to give an intuitive explanation of this. So as a low-level explanation, what you can think in the effective one-body formalism, where you map the problem of 2 black holes that are colliding to an effective problem when you have essentially a test particle which is orbiting around a big black hole. It's the same that you do in Newtonian gravity, where you solve the Kepler problem, but now it's it's the version of steroids in GR. Of course, this was pioneered by Thibaut Damour and Alessandra Buonanno and many other people. Or alternatively, you can think about a large mass ratio in spiral, where you have a supermassive black hole and a solar mass black hole. And so in this case, you can start thinking in terms of geodesics, and so you can start thinking in terms of effective potential in the radial equation. So this, of course, is the effective potential of Schwarzschild. You all know this. You all know that here there is a centrifugal barrier. So imagine that the motion of this binary is described by this particle on a geodesics. So what's happening is that there is emission through gravitational waves, and so the orbit is shrinking. So the particle is sit on a quasi-circular orbit, and the orbit moves towards the black hole. So J dot is the emission of angular momentum through gravitational waves, and the particle moves inwards and inwards and inwards. But what's happening is that when it moves inwards, not only this dot changes, but also the shape of the potential changes, because you're emitting angular momentum. So the centrifugal barrier has to go down. It's pretty, level 0 dynamics in GR. So the peak of the potential barrier is going down, down, and down, and at a certain point, you don't have a peak anymore. So the potential is turned from something which can sustain bound orbits like this to something which just goes down. So there is no way of sustaining a bound orbit. And when this happens, so you have to imagine the particle going around, gravitational waves are emitted, and when the peak of the potential, the particle falls directly into the black hole. And this is the plunge phase. Level 0 explanation based on essentially a paper by Buonanno and Damour and Ori Thorne in the early 2000s. But of course, this is the level 0 explanation, and it's not what fully predicts a waveform. There has been more progress recently, but this phase is so complicated that upgrades of this can help you explain the conservative dynamics, but the radiation reaction part is still not fully understood. So what we do now is just we calibrate to numerical simulation. So you have some phenomenological parameters that you tune to your numerical simulations. Yeah. I don't know where's the cube.
It's about the inner more stable orbit. So my understanding was that if you do, for example, post-Newtonian or post-Minkowski, you can actually get some of this plunge phase. You don't need to. It's not fully numerical GR, so you can actually use and so in this graph of yours, for example, until when can I use post-Newtonian and post-Minkowski, and when do I need to go to numerical?
So this is in full EOB with the best models that we have now. So post-Newtonian is resummed in some particular way, but it's hard to say in this. But I think that.
But I thought it's also in the plunge phase. You can get quite a bit of the plunge phase with post-Newtonian.
You can in the conservative part, but the radiative part is much more complicated. So the waveform needs, so in the conservative part, you can get along with this until, let's say, one orbit to ISCO, or maybe ISCO itself. But the point is that the piece of the waveform that you have to predict needs these non-quasi-circular corrections that are extracted from an R at this point.
And they cannot be, okay.
But for example, what people are doing is that they're starting from self-force theory. So self-force gives you an expansion in the mass ratio, and they're basically trying to understand what terms we would predict from a full GR computation in self-force, and then tune the coefficient that they miss from numerical relativity, because for the moment they still cannot compute all. But post-Minkowski and self-force are very promising to actually have an analytical prediction of this. Okay, so what you do is that you add there are some coefficients in our model which are completely phenomenological. They capture a bit the features of the waveform, and the first thing that was done was just to measure the deviations from this coefficient. So this should be compatible with 0. And in the first detection paper, you can see several constraints of this, and everything is compatible with GR. There's been a bit of progress here recently. There is a paper by Elisa Maggio. She works at AI with Alessandra. So what they do in the EOB is that at the peak of the waveform, you have a certain prediction for the amplitude and the frequency. And so what you can do is that you take the amplitude of the waveform and you parameterize the deviation by 1 plus delta amplitude and 1 plus delta omega. And so here I'm showing when I vary delta omega or when I vary delta A, this is how the waveform changes. And so you can also do this. It's still like kind of phenomenological. I'm just taking the point prediction here, and I'm trying to see how much the data can deviate from that. And then you get some constraints on these deviation parameters. This is interesting. It's just a null test, essentially, but it doesn't teach you a lot for the moment, just because we don't have a good understanding in GR of this phase. A good analytical understanding in GR of this phase. And then there is the third part, which I'm typically mostly excited about, which is the Ringdown. And the nice thing about the Ringdown is that we have a much more strong analytical understanding. So essentially, what you have to the Ringdown, you can think of it as the relaxation of the final object. So these two objects have merged. They form a very distorted object. And so what the distorted object does is that it starts to vibrate and to emit gravitational waves until it relaxes towards a stationary state. And the stationary state is Kerr. It does so by vibrating according to its own characteristic frequencies, which are the quasi-normal modes, and they're predicted by perturbation theory, and you need some input also from an R. So the waveform looks like this. It's just a superposition of damped sinusoid. So you have the oscillating part and a damping part, and then of course you have some amplitude excitation factor and some angular factor. The nice thing of this is that by the Noether theorem in GR, all these frequencies and damping times that enter the waveforms, so that you have a tower of frequencies and damping times. You have an countable infinity of them, but they're all predicted by just 2 parameters. Well, 3, if you believe in charges. The mass, the spin, and the charge. I'm going to talk about the charge later on, actually. But, in astrophysics, people say, no, there is no charge. It gets emitted away, blah, blah, blah. And so we only look at mass and spin. So you have 2 parameters determining an infinite number of parameters. And, of course, you can use... So imagine you measure a frequency and a damping time. You can use them to draw a band in a mass spin plot. And then as soon as you measure another frequency, you can draw another band and see if these bands intersect. If they do, it means that the different frequencies that you're extracting from the data, they all give consistent measurements for the mass and the spin. If they don't, then there's something wrong with the Noether theorem, or this is not a Kerr black hole, and there are many possibilities here. See, this is what's called black hole spectroscopy and testing the Noether theorem. There is a question there.
So can LIGO measure anything more than the fundamental mode, L equals M equals 2 and N
So
equals 0?
LIGO and Virgo can, in principle, measure more than the fundamental quasi-normal mode. There is a hot debate about this. There are people claiming that we have seen an overtone. There are people saying that we have seen a fundamental. So here there are indices. So L and M are the standard angular indices, and N is a radial index, which is called the overtone index. So there are people claiming that we have seen, and the dominant mode here is the L equal 2, M equal 2, just because the quadrupolar mode is the strongest one. There are people claiming that we have seen the L equal 3 mode, and people that claim that we have seen the N equal 1 mode. So my take on that is that
There are also people claiming they've seen N equals 1 through 7. No,
no, that's on numerical simulation.
that's the numerical.
So that's the Kolsky group, which is a model on numerical simulations. I have a few papers on that too.
Okay.
We can discuss that. It's a bit technical. So the point with overtones is that I don't believe in the model. So I think that the model they're using is not valid just because they are starting from the peak, assuming the mass and the spin you get at the end of the coalescence. So when you start to fit the waveform at the peak, you're still going to have a strong emission of mass and spin. Actually, you're emitting like 8% of the spin. So you cannot assume that the spin of the black hole at the peak is the same that you're going to have asymptotically, while they do. So I just don't believe in the model. For the L equal 3 mode, there are a lot of systematics, and it's just not a robust detection for the moment. But it's something that with future detections we hope to measure.
And is Lisa supposed to get you? How confident are we that we could?
I have a plot on that at the end.
Okay, and one more question, just very naively, when you look at all these ring downs, there's like 3-4 oscillations in there, and these overtones, they're all damped sinusoids. So how can you know if you're overfitting or not? I mean, because if you give me, like 5 damped sinusoids, I can fit that to any 4 hops with an exponential.
We have a 56 pages paper on that. On the archive, I can give. Well, there is a reference somewhere, but I can also give you the reference.
But
so
you're sure
it's a very delicate. I agree. It's a very.
But is doable?
It is.
What's the real?
It is doable under certain conditions, but it is a delicate business. I completely agree. So what you can do is that there are. So for example, these amplitudes from perturbation theory are predicted to be constants. So you can do some self consistency checks to see if you're overfitting or not.
Okay, but without reading the 56 pages, can I just get the one sentence conclusion? So what do we think we can really do with LIGO, and what do we think we can really do with Lisa, like that we're definitely going to do? That's like a really interesting question. I can't get a straight answer, so I'd love to get one. So
with LIGO and Virgo, what we hope to do is that we will maybe have a detection of 2 fundamental modes, the 220 and the 330, if the mass ratio is right. It depends on how far in the upgrades the detectors will go. It's still kind of uncertain, and also this depends on the population you're observing, and the population we are learning now. We have 90 detections now. We are gonna have 500 in a couple of years. So it's a question that depends on the sensitivity that LIGO and Virgo and Cagra will reach, and also the population we are gonna see. But I think it is quite likely that we are gonna get few percent tests of the no-Earth theorem with these detections. With Lisa, you're gonna do precision physics. So with Lisa, you're gonna get 10 to the minus 3 precision, and you're going to observe hopefully more than 2 modes, even 3. But it is not. So yeah, I think the general picture is understood, but there are a lot of details which depends on the things that we are actually observing right now.
Different band.
Yeah.
So so you wouldn't be able to learn. You wouldn't be able to learn anything. Thank you. Anything from actually the detection that you have from LIGO itself, because in a completely different band.
So if you assume that mass is just a scaling parameter in GR, so what you will observe in Lisa, it's supermassive black holes. So the mass is much higher because the frequency is much lower, but the morphology is the same. If you have 2 supermassive black holes or two tensor massive black holes, the ring down is the same because the mass just is a scaling parameter.
But then there's a question of the different species of object. If you
I agree. No, that's what I wanted to talk about in the later part. Yeah, I have a section of the talk on that.
Okay. Well,
because it's a different curvature regime.
Okay, good. So what about the next generations, Einstein?
I also have.
Good. Thank you.
Thanks. Okay. So you all know this. We have measured the fundamental one that we all agree about. This was done in the first paper. So the black is the prediction from GR, and there are several contours, because what we are doing is that we are doing the measurement first here and then later and later and later, and see these are consistent. Of course, if you do it later, you lose a lot of the signal, and so in the end, you're going to get very wide bands. So these are two-dimensional probability contours for the frequency and the damping times. It means that everything inside this contour is consistent with the data. So the black is the prediction, and you see that the violet one, which is what we think should be the prediction, overlaps nicely with the black one. So it means that we are measuring what we expect to be the fundamental quasi-normal modes. This analysis was actually not, so there were minor technical issues. So what we did with my supervisor and collaborators is that we proposed a new formalism, doing it in the time domain, and so improving this measurement a bit. So the idea here is that in a time domain approach, so first, you just look at your data fitting some damped sinusoid, and you get some agnostic frequency reconstruction. So I measure something which has a frequency of around 250 Hertz and a damping time that peaks at 4 milliseconds. This is just agnostic, whatever there is in the data. And then I compare this with all the spectrum that's predicted by GR. So GR predicts a tower of quasi-normal modes, and each of these ellipses is a different quasi-normal mode. And then you check with which modes your reconstruction agrees. So in this case, the agnostic reconstruction is agreeing the most with the quadrupolar mode, which is what we already discussed. And so basically, you formulate black hole spectroscopy as a Bayesian, in a Bayesian formulation. Okay, and actually, if you're a student which is interested to learn about this, I have a Python package which is public, and it's the one which is officially used by the collaboration for all these measurements. There are even tutorials, and you can measure a black hole vibrate on your laptop in 3 minutes, which I think is cool.
Can you go back to the phase plan?
Can you please explain what are the colored circles?
So,
What do
the
they
color
correspond
circles
to?
are, for example, these are L equal 2, M equal 2. So these are all the L equal 2 modes. So
Yeah,
M equal 2, M equal 1, M equal 0, and the other is L equal 3.
Right, but each for a given black hole mass and
No,
spin,
sorry,
these are
this is a
numbers.
single black hole, and they are ellipses because there is an uncertainty on the mass and the spin, if you wish. So there is also an uncertainty on the frequency that GR is actually predicting. So these folding in the uncertainty.
So you look at a particular black hole event, you just, without assuming anything, you just extract the frequency. That's the black thing. And then you also have some measurement of the mass and spin
let's say the full waveform.
from the numerical GR waveform that you fit. And there's an uncertainty in that. And then you figure out which.
Yeah, it's just the uncertainty in the data, because these are computed by looking at reconstructions of the waveform from the data. And for example, what you can see is that, well, on this plot, you cannot see it very well, but you can see that still the reconstruction that we do, it overlaps with many different modes, not just with one. So the most probable is the quadrupolar mode, but we actually don't know.
Yeah, that's a very cool plot. And so just one last question. If you were to, why are you getting a single frequency? Presumably you're also getting more frequencies out of this signal?
I'm looking at late enough where the linear perturbation regime is supposed to be valid, and so that then you get only, well, you can get two, but the second one is going to have a huge uncertainty, and you're not going to see anything.
Okay, thank you. This is very helpful.
Yeah, I have more than that. Hopefully they're more clear. Okay, so this is going slightly different than I was expecting, but I think it's fine. The discussion is nice. So there was a bonus part, which I think it's a kind of interesting point. So I showed you that we are measuring a frequency of 250 Hertz and a damping time, so the time at which the system relaxes, of 4 milliseconds. Well, who cares, right? What do these numbers mean? So if you start thinking about what they mean, so you can think, how fast is the return to equilibrium? The answer is very fast. So you have to imagine that you have systems of hundreds of kilometers, 300 of kilometers. It's 1/3 of France. That it's perturbed, it's vibrating, and 4 milliseconds, completely silent. It's mind-blowing. If you think about it, 1/3 of France, that in 4 milliseconds, it's mind-blowing, right? How mind-blowing it is? Can we quantify how mind-blowing it is? So the way I like to put it, if you think about, when I think about systems going to equilibrium, I think about information emission. And there is a very nice paper by Bekenstein where actually it derives an upper, so if you assume causality and let's say all the standard laws of GR and thermodynamics, there is an upper bound on the average rate of information emission that you can get from the system. And so And in another paper, Hod translated this bound on information emission on black holes. So basically, the information emission rate can be written something like this. So 1 over pi, and then you have kappa bt, where T is the Hawking temperature. And the numerator is simply h bar and omega I, where omega I is the inverse of the damping time. So this is just quantifying, let's say, thermal emission against the emission that you're getting gravitational waves. And the ratio of these two is essentially how fast the system is emitting information. So for normal systems in the laboratory, these 10 to the minus 11. For the black hole that we had, we have a paper on this here. So we actually measured, so the prediction from GR would be the black curve. And what we actually measured was a posterior distribution. So this normalized to 1, so the bound tells you that you have to be below 1. What we actually measured was around 0.6, which is kind of very, well, there is a bit which goes above 1, but most of the bulk of it is between 0.6 and 0.8, which tells you that basically this is the fastest the fastest relaxating object that we have ever observed. Anything, unless maybe if you take quantum system close to critical points in phase transitions. Otherwise, if you think classically, this is the fastest ever relaxating object that we have observed. I think there is a question.
Could you clarify by what you mean by information here per se?
Well, in this case, it's just you're emitting gravitational you're emitting radiation away, and so this contains information about the mass and the spin of the system. So
so some sort of classical information.
Yeah, it is classical.
So, but normally to compute that, you need some distribution. You're computing p log p for some distribution.
Well,
so what does it mean here?
Well,
or is it log of one?
Here you just assume area equal entropy, essentially. You just assume that it's a Kerr black hole and area equal entropy. That's it.
Okay, I don't follow that at all.
Well, so you can compute classically you can compute the entropy of the black hole, right?
Yeah.
As proportional to the area. And then you can express in terms of the mass and the spin of the black hole. And so you can also compute how fast you are emitting this information. So if the mass and the spins are changing because you're emitting away, you can compute how fast.
The area is changing.
Essentially, yes.
And then you change area to an entropy by area over 4g Newton. So that's the calculation.
Yeah.
Okay.
No, it's nothing more. Of course, it's
because you said something about information theory in the next slide, which is why I got confused.
No. So well, this is emitting information. It's at a classical level, but you're still emitting information.
Well, it's okay.
So to me, this is non-trivial.
It's emitting waves carrying energy and spin.
Yeah.
And you want to interpret that as saying it's carrying information about something.
I can interpret it as emitting information, right? As any other system. So let me give you. So why is this non-trivial? So first of all, because this bound that is predicted here is not something that normal classical systems would get. The bound saturation is a universal behavioral system close to quantum critical point. So if you open the book of Sachdev, this one of the first things it tells about quantum phase transitions, and the fact that the black holes actually saturate these bounds, it's actually non-trivial. Of course, it's one of the many puzzling things about black hole thermodynamics. I'm not saying there's a new prediction here; it's just a reformulation of the prediction. But I think it's a very nice way of understanding how crazy these systems are and how crazy are the systems that we observe. And yeah, it also is connected to something that probably is known in the high energy physics, which is the viscosity entropy bounds. But okay, so beyond the Kerr spectrum, what have we measured? So what we care about is not actually the Kerr spectrum, but if we can go beyond that, right? So one thing that you can do is that you can take the predictions from a Kerr black hole, and then you put some parametric deviation. So this is the thing predicted by GR. I put 1 plus delta omega, delta tau, and I try to measure these delta omega and delta tau. And we have done that, and the result here is that omega is, for example, this is the deviation on the fundamental mode. It's compatible with 0, with an uncertainty of, let's say, more or less 10%, 7% here, which, is nice and fine, but, how do I interpret this? Okay, this is just telling me that for the moment, we observe a spectrum which is consistent with GR at the level of 5–10%. That's it. Ideally, one would like to connect to predictions from effective field theories, higher order curvature of gravity, or just to start to connect these numbers to something which is more from the fundamental physics perspective. And so what are the fundamental physics implications of this? You cannot do much with that parameterization, but you can do progress if you start thinking about, the problem is that when you go beyond GR, you cannot compute things for highly spinning black holes, because typically these black holes are very highly spinning. They are 0.7 of the maximum rate. But what you can do is that you can think about an expansion in the black hole speed. So you take your spectrum. This is going to be a trivial function of the mass. And then you can do a polynomial expansion in the spin. Chi is the spin of the black hole. And then you have some coefficients which represent the prediction of GR. And these are numerical constants. So now what you can do is that you can start to put deviations at each order in spin controlled by some gamma parameter. And this gamma parameter is essentially what appears in your action. So if you have an alternative theory of gravity, you're going to have some new fundamental length scale, if you think about in an effective field theory point of view. And this length scale is going to enter with some power p, which, if you have Gauss-Bonnet gravity, this p is going to be equal to 4. If you have Lorentz vibrating gravity, p is going to be 0, and so on. So, in this way, you can rephrase your constraints in terms of a parameter which you can then connect to an action, which is nice. And also now the point is that also these delta omega things that you're measuring, they will also be numerical constants, so they are independent of the signals, that you can just stack together a bunch of different signals. And for example, is the landscape of the theories that one might consider. So for p equals 0, you have Lorentz vibrating gravity. P equals 2, you have a charge. P equals 4, you have quadratic gravity. P equals 6, you start to have effective field theories. So what I'm saying is that there's a whole bunches of classes of theories which you can just map to that parameterization with some specific values of this coefficient P. And so we did this for, so I did this in a paper for different theories. And so for things that have scalar deviations, you can measure, let's say, the non-spinning term, so the deviation from the non-spinning term for a scalar theory, and you get something which is consistent at the 5% level. You can do, the nice thing is that with this parameterization is smart, so you actually get a boost in the sensitivity to beyond GR deviations. You can do this for, let's say, quadratic gravity, where you get a bound on the length scale of new physics. So if you have an action which has scaling as a quadratic gravity theory, then you can bound the length scale of this to be smaller than 35 kilometers, which is kind of compatible with other experiments. So it is competitive, and also it will improve very fast with new observing runs. And also, if you have predictions from effective field theory, you can bound this new length scale to be smaller than 40 kilometers. Right. So the nice thing about this is that there is a whole industry of people that are now starting to compute quasi-orbital modes in alternative theories of gravity. And what they compute is that they compute the expansion in spin. So they compute the non-spinning in beyond GR, then they compute the linear spinning term, quadratic spin, and so on. And with this, you can actually incorporate all of this quite nicely. This has already been done at the linear level by Hector Silva and collaborators. So he took an effective theory of gravity for which we had prediction of the linear spin, and we did the analysis. And still now the length scale is, let's say, order of smaller than 40 kilometers. Of course, these are big objects, so you can only bound orders of tens of kilometers length scale. And now here is a whole map. There is a lot of work being done, for example, by Pablo Cano and Alejandro Ruiz Perez and collaborators that are computing this for quadratic gravity and effective field theories. I think they reached up to second order for the quasi-orbital modes, but they have a very promising scheme to go actually to much higher rotation rates. Then, of course, you have Einstein-Diraton Gauss-Bonnet and dynamical Chern-Simons predictions. And so the idea is that now we are incorporating all of this. We are redoing the analysis with these quadratic ordering spin corrections and see how much they improve the measurement. And what people already mentioned, in the end, what we would like to do actually is to do full numerical relativity simulations in beyond GR. This is a recent paper by the group of Luis Lehner and Pau Figueras, where they actually did manage to evolve in an effective field theory, essentially without any approximation. They use a very clever numerical scheme. So there is a much work going around here by Justin Ripley, Will East, Hector Silva, and the group of Elvi Witek, and a lot of other people. But now we are starting to be able to actually simulate consistently waveforms in beyond GR theories. And so these promises to give a boost to beyond GR searches in the future. As a critical point, gravitational wave observations measure scales of kilometers. If you think about higher curvature corrections, you're expecting this to kick in at the Planck scale, right? Why are you doing this? Who cares? So the point is that this is a valid argument. It's a valid argument that we are not expecting higher curvature corrections around classical objects. But the point is that the gravitational wave experiments did a jump of 6 orders of magnitudes in the redshift and 13 in the curvature compared to any other previous experiment. It's a huge gap in the strength parameter of your theory. So from an experimental point of view, this huge jump in the parameter space of your theory is enough to justify an agnostic observational approach and try to search for these deviations. And we use effective field theory just as an indicator of, there's an infinite parameter space of things that we could search in the data. So we just use effective field theory to give us a guidance of what are the things that we should be searching for. But in the end, if you're really interested about higher curvature corrections, what you want is not big black holes. You don't want to go to milliards and Lisa band. You don't want to go to a supermassive black hole which has the density of water. You want to go to higher frequencies. If something funny is going to happen in terms of this, so if there are no horizons, it's a quantum structure and whatever. This is independent if you look at Lisa or LIGO in Virgo or Einstein telescope or whatever. But if you think about things which actually scale with curvature, going to higher frequency is the right direction to go. And now actually, so there is a nice review paper here, and there is a website about an initiative which is called Ultra High Frequency Gravitational Wave Initiative. So there are people who are already there are already experiments looking at gigahertz gravitational waves and megahertz gravitational waves. And this will give you hints about, phase transition, axions, primordial black holes, which are very, very much smaller than a solar mass black hole. And there are people starting to, think about motivation, the science case for these kinds of detectors. So there is an experiment in Australia, a few in the US, and more activity is being done here. I think this is very interesting and very promising. I understand that we want to do LISA for astrophysics, but if you're thinking about fundamental physics, to me, this is the way to go for a simple reason that there is no astrophysical background. There is nothing in astrophysics that will give you a signal at gigahertz. So if you see something, whatever you see, it's new physics, which is pretty cool. Maybe it's a primordial black hole, so it's not super exotic in physics, but it is in physics. Okay, so, yeah, please.
Is it, I have no idea how you would measure this. Is it the same kind of setup in LIGO, et cetera, or do you need something completely different?
In Australia, what they're doing is that they're doing a smarter version of the bars, where they have a very sensitive readout. Or another thing that you can think about is, so there are these experiments for searching dark matter, where what you do is that you take a room, you put a gigantic magnetic field, and you hope that if there's an axion passing, it will couple to the photons. You will see photons essentially popping out of nowhere. You can do the same exact search with gravitational wave. There is a graviton-photon vertex, right? So you can just put a gigantic magnetic field, you put a graviton, at a certain point it interacts with the magnetic field, and you start to see photons. And the cool thing about this is that you don't need to build an experiment. There are already these experiments, but they're using them for dark matter. So you just convert you take LHC magnets, you put them there, and you just reuse that experiment in principle. Then there are optical cavities. Actually, the nice thing about this is that there are probably tens of different proposals and experiments running on this. So it's still up for discussion.
It sounds like a much smaller scale.
Sorry, yeah. But the bars are like probably room size experiments, and the optical cavities are tabletop. So
I mean, like money wise, like it's not, you need to invest the same amount of money.
So you don't need 2 billion like for Einstein telescope. You need probably tens of millions or something.
Doesn't that mean the sensitivity is kind of rubbish? Or?
No. So it's a tricky point because it depends what does it mean, rubbish, right? So the sensitivity. No. What I mean is that for gravitational waves, there are astrophysical sources, so we know kind of what to expect, and so where the sensitivity needs to be for these sources. But if you go at very high frequency where there is the unknown, you don't know what's required. It depends on a lot of assumptions. But no, I think, of course, they're still in an initial phase, but the sensitivity is improving at a very interesting rate. But there is a review of they did a workshop in Trieste. I think they did a workshop at CISA in Trieste, and they have a review on that. And there's going to be a workshop at CERN in December this year. So if you want to have a look at, if you're interested about this, you can have a look at this review.
My question is about the coupling.
The coupling of what, sorry?
The gravitational coupling it would be between the photon and the graviton.
That's
it's
why
heavily suppressed.
You need Tesla magnetic field.
That's why I was asking.
Okay, so this was supposed to be half of my talk instead of 3/4, which is fine. So so I will briefly sketch what we have been doing on several other things. Try to get to something which could be more interesting. So black hole charges. So if you talk to anyone doing astrophysics or close to astrophysics, they will say, we don't need black hole charges. There are no charges of black hole because there are very well-known astrophysical mechanisms for which black holes will lose electric charge. But I think there are several interesting points to be made about charges. So first of all, the O'Hare conjecture tells you that the most general family of solutions in GR also has charges. So even from a mathematical consistency point of view, we want to at least try to include those and see if the observations are still consistent. And also, we have a prediction from astrophysics, which is the charge is 0. Can we confirm it observationally? Can we try to actually measure this? And also, there are fundamental physics motivations. There are models of mini-charge dark matter. There could be magnetic charge, right? You could have primordial magnetic monopoles, which are very heavy. And so this will give magnetic charge to black holes. And then you can have exotic compact objects, which in principle might be charged. And there is, of course, scalar vector tensor gravity and topological induced charge, many things. But in general, it's a very valuable test bed for beyond Kerr. So what we did with Oscar Diaz and George Santos and other people is to predict essentially the well, they had a paper on predicting the spectrum, so we tabulated it. And so we built essentially the GR prediction for the spectrum when a black hole has a charge. And then we redid all the analysis. Long story short, we can put kind of an upper bound on the maximum amount of charge of black holes. So this is the charge, this is the probability of having the charge. And essentially you can put an upper bound to 0.2 to be, the charge has to be smaller than 0.4 or 0.5 of the maximum allowed. So the charge is normalized between 0 and 1. So you can see that under certain assumptions, these black holes are not charged more than 50%. And if you want to go beyond upper bounds, even these detectors at the sign sensitivity, if the charge is high enough, you will actually be able to measure it from the Ringdown. So if you have a charge of half of the maximum, you will actually see a clear peak here. And so you will be able to measure it. You can also do dipolar emission. You can constrain dipolar emission in the spiral and also get similar bounds. In the end, what we want to do, and actually what we are doing, is that you want full numerical simulations of black holes with charges. And this was done by Gabriele Bozzola and Pascalidis. And now we are working with them to include these predictions into our searches and see if the black holes we are observing actually have charge and at which level. I also wanted to flash a lot of work that has been going on and led by David Perenigues. So if you look at just the Ringdown, the phenomenology is kind of boring. So it's kind of similar to what you get in GR, because a single black hole having electric charge or magnetic charge in terms of the Ringdown is the same, because there is a duality transformation between the two. But as soon as you put more than one electric black hole, so if you have two dionic black holes, then the phenomenology is much richer. And they're actually going to put a paper out on this in a few days, where they explore a bit this.
When you do these full numerical simulations, it's there's some electromagnetic transport as well. And
there's.
Okay, so you're taking into account. Do you see? So in general, sorry. Do you see? For a sizable charge, I don't know, 0.2, whatever. Do you see that the electromagnetic counterpart becomes
large enough that you would be able to see this also electromagnetically?
The problem
or?
with that is that the electromagnetic signal has to travel through interstellar medium, and the plasma frequency typically prevents it to pass it through.
Ah, good. So you know that
this would
yeah.
be dark. So they would have an electromagnetic emission, but it's very hard to detect it on Earth. So that's why we need to model this in gravitational waves. Otherwise, the electromagnetic part would be much stronger.
So let's say you model you don't model it with using the full Kerr-Newman waveform, then you would find that there's some mismatch, and in particular that you're losing energy that you haven't seen. Basically.
Yeah. So I don't have this plot here, but there is in this paper here we actually do that. We see if we model things as in GR and these black holes have a charge, what are the wrong things that we
Cool.
Okay. Right. So in the last 9 minutes, I will briefly say, okay, this is not more than saying it's discuss ideas about how can we access horizon physics from gravitational waves. Because you all know that the Ringdown gives you, it's an expression of the light ring structure, of the peak of the potential, and not a lot of the horizon. So you need something exotic to probe horizon physics. So the most studied, okay, this is a bit cut, but one thing which was very studied is the presence of echo. So if you don't have an horizon here, but you have a reflecting barrier, what happens is that instead of the single nice Ringdown that you get, you will get multiple emissions. So this is the main signal, and then you get repeated bursts of gravitational waves. Of course, there are assumptions on the scrambling that the way we'll do it. It's very complicated to get consistent models, but we expect, let's say, multiple peaks. There have been a lot of claims about this, especially by the group of Shorty. From an observer point of view, we redid the analysis within the LIGO-Vico collaboration, both using a model by Afshordi and both using completely unmodeled, so just coherent power among the detectors. And both things tells you that everything is within measurement errors, and there's nothing. For now, there is no evidence for echoes. Then there are some more, you can start to get a bit more crazy. So there is this, of course, there is the horizon area quantization proposal, but this is gonna affect the horizon, typically not the Ringdown. If you assume that the long range Ringdown modifications are also proportional to the horizon quantization frequency, then in principle, it's a prediction of this model. It's a far-fetched model, but the good thing about this model is that at least it's testable by LIGO-Vico Cagra, because when you have the spectrum dictated by horizon quantization, it doesn't have a continuous limit to GR. It's a completely disconnected from GR, and so it's very easy to test it. So in the next few years, these kind of crazy proposals, it will be very easy to test. Near extremal black holes would be actually an incredible probe of horizon physics, because in that case, the light ring goes towards the horizon. Yeah.
Rush, take a couple more minutes.
Yeah. So I think we are going to hear more about this in near extremal black holes. The question here is the rates in gravitational waves. We don't know if to expect near extremal black holes, at least in this spectrum. For LISA, for supermassive black holes, you expect much larger spins. And another point which was discussed recently was spectral instabilities. So this it's a simple mathematical statement. The operator dictating the quasi-orbital modes, it's not self-adjoint. For self-adjoint operators, you have standard triangular inequalities, which tell you that if the potential is perturbed by an epsilon, then the eigenvalues have to be perturbed by an epsilon. But this is not true for non-self-adjoint operators. And the one of the quasi-orbital modes, it's in this class. So the idea is, if I take my potential and I have a bump somewhere, what happens to the spectrum? This could be dark matter, it could be whatever modification. The result is that the spectrum is completely destabilized. So the red one are the quasi-orbital modes predicted by GR, and the lines are where the quasi-orbital modes are migrating, where you put this kind of deviations. So basically, as soon as you put even a 10 to the minus 3 modification kind of far from the black hole, the spectrum changes completely from the vertical line, lines to something which is far away from the GR limit. And people were saying, sorry?
Where is the bump from this?
So, okay, for this plot, actually, I was assuming a sinusoidal perturbation to the potential with a strength of 10 to the minus 3, just because this is a nice plot and it gives you the idea. But
the wave numbers and what is the wave K?
Yeah.
What's the unit of K? Is it the horizon scale?
yeah, it's a mass scale. Yeah, but so the point is that this is very sensitive to what exact modifications you put. The nice thing is the comforting thing is that even if the spectrum changes completely, the waveform does not. So so this is a bad plot, but the nice thing is that it's from 1996. So people already kind of knew that this behavior would appear in the spectrum, but they also knew that the waveform only at late times, there is a very, very, very tiny change. So the point is that even if the spectrum is destabilized, it doesn't mean that the signal will be completely different, because the spectrum is a property of, it's the poles of the green function. The waveform is the full prediction which folds in causality and all the dynamical structure of GR. But still, people were saying this might be a probe into high-frequency space-time fluctuations or Planck scale, because you have basically they were saying you have an epsilon change in the potential, which is not it's not going to turn into an epsilon change in the spectrum. Yeah. So in principle, it's interesting. My question is, what is the solution of the Einstein equations that gives you that bump in the potential? Because in principle, you should modify the stress energy tensor. It's not just putting a bump in the potential. It's much more complicated than that. So what we tried to do in the last few months is that we teamed up with a guy, Luca Marchetti, he did a PhD with Daniele Oriti. He works on loop quantum gravity models. And so we said, okay, take a loop quantum gravity metric, even if you don't believe that, right? It's an example of a metric with which I can compute quasi-normal modes, and it has fundamental physics principles. If I take this metric, which is from this paper here by Gambini, Olmedo, and Pullin, do I see these instabilities? And the answer is no. So here you are putting an epsilon change in the epsilon change here is just that loop quantum gravity is introducing Planck length corrections, but essentially the deviation that we see in the spectrum are proportional to epsilon. So the point is that it is true that the quasi-normal mode spectrum is unstable, but the point is there are some classes of modifications which will give you crazy instabilities, and there are some other classes of modifications that don't have to give you instabilities. So it's very sensitive to actually what you're doing. Okay, this was a recap of what you. Oh yeah. 5 minutes. Okay, cool. So just to give you a wrap up of current observations, what do we know? We know that in the fundamental mode, we can bound deviations of GR by 5–10%. We know that we have certain bounds on the spin-induced quadrupole moment, and we know that there are no echoes for now. We can bound new length scales to be smaller than 40 kilometers. We cannot really know if these black holes are charged or not, and we cannot exclude naive area quantization models that affect the horizon. This is what we know now. What we will be able to know with future detectors. So just to, when gravitational waves are incredible. These are extremely interesting science, but this is what we measure now. So the black is actually the output of the interferometer before touching it, and the yellow is the ring-down signal we're observing. This is the level of, this is the level of craziness of this kind of analysis. Of course, once you understand the noise, you characterize its correlation function. From this, you can get to something like this. So you have taken into account the noise properties, and so you can extract some signal here, which now it looks much more reasonable. It's actually compatible with the predictions of GR. But this is what we measure. In the future, this is what we are going to be measuring. So with LIGO at advanced sensitivity, it's still very noisy. It's much less noisy than before, but it's still very noisy. But with Cosmic Explorer or Einstein telescope, this is the untouched, unwhitened signal from the detector. You can see a gravitational wave by high. Because this, of course, has a SNR of 1,000. But without whitening the signals, this is strained 10 to the minus 21. So you will just be able to see the waves. And of course, if you characterize the noises. So this is how incredible the science with next generation detectors is going to be. What does it mean in terms of black hole spectroscopy? We're going to get signals with SNRs of hundreds. And so you get, so what Alex was asking before, how does this plot looks like when I have much more sensitive detection? So for the moment, this is what we are measuring, right? It's the same plot as before. I have the stars are the spectral prediction from GR. There are different frequencies and different damping times for all the modes. And this is my reconstruction now. In the future, this reconstruction will turn into this very, very small. We are going to pinpoint if GR is correct, we are going to pinpoint the fundamental mode, and then we are going to measure another one. In this case, is the helical 3. It's still with a not incredible sensitivity, but the first one is going to be very precise. And this with a signal to noise ratio of 40, which is in principle reachable by these detectors at design sensitivity. With Cosmic Explorer and Einstein telescope, this is going to shrink by a factor of 10. So you will have something like this also on the other mode. So the prospects for this are kind of incredible. If you care about other things, so I think there is a case to be made that for many interesting measurements, there is just a space supremacy. So if you look at LIDA measurements, so here I'm plotting the relative improvement compared to what we measure now for four key observables, the horizon flux, which is something that's very interesting, right? So how much of these gravitational waves is going in the black hole, the tidal deformability, the spin-induced quadrupole moment, and the quasi-normal modes deviation. So for Einstein telescope, you're going to get a factor of 10, maybe 100 for all these key quantities, which is very important, right? But for LISA, and especially, so for LISA, you're going to improve all of this if you look at supermassive black holes. But if you look at extreme mass ratio in spirals, so a small object orbiting around a very big one, this is going to jump, especially the horizon flux. It's going to be 10 to the minus 6 more sensitive to what we have now. It's a gigantic leap. And for quasi-normal modes, actually, we don't know with MRIS. And I'll conclude the talk just by mentioning this thing about horizon flux. So horizon flux just means that, when these objects are emitting gravitational waves, they mostly go to infinity, but of course, part of them will also fall into the black holes. For now, this effect is very, very small. It's actually essentially unmeasurable. So you can have a measurement which is like, so 1 is 100% of the absorption, and we measure 1 plus or minus 20. So if the absorption is off by 2,000 times the one predicted by GR, then we are going to measure something. But of course, it's just telling you that the current precision, you're just not getting there. But with LISA, you're going to have a 10 to the minus 6 improvement. And so you're going to have a very, very precise measurement of the flux absorbed by the horizons of the black hole, which is actually what you want if you want to think about exotic compact objects. There is a lot of work on this. Most of this is based on perturbation theory. So lots of work to be done on the modeling side, even in GR. But I think probably this, to me, this is the most promising measurement that we will be able to do with this. And yeah, I hope I convinced that now with gravitational waves we can test the gravity paradigm and search for new physics in a large number of different ways. Hopefully, we're gonna be able to infer the reason properties. Who knows? And yeah, thanks.
You mentioned that there were about 100 events and that the average A parameter was 0.7.
Yep.
What is the standard deviation in A in the events?
So if you measure it assuming the full emission, I think you get something like 0.7 plus or minus 10% or something like this, maybe more, but this in the papers, but let's say order of 10%.
And I have another question. You mentioned that there is some problem related to the finding deviations to quasi-normal modes because A is 0.7. Can you explain what the problem is?
So it's not an intrinsic problem. It's just that when you go beyond GR, it's easy to do Schwarzschild. It's easy to do spherically symmetric solutions in beyond GR. But then when you turn on the spin, there is coupling between modes and a lot of, also in beyond GR, you don't have isospectrality. So you have two families of modes. It's a whole lot of complications. So what people now are able to do, this paper by Pablo Cano and also by Leonardo Guartieri and their collaborators, is that they do a small spin expansion. So they look at Schwarzschild plus linear corrections in the spin. So you have A times some small correction. And then you can go, with this, you can go to quadratic order and so on. And so they're doing this in a perturbative expansion. Of course, with quadratic terms, you don't get to 0.7. You get maybe to 0.1, 0.2. So in the last paper of Pablo Cano, they have in the metric part, they can go essentially up to arbitrary spins. But for the quasi-normal modes, it's much trickier. So I think there are good promises with their techniques to go to much higher spins. But for the moment, we still have things that are accurate probably to 0.2, not 0.7.
They have arguments that.
Oh, yeah. Can I just follow? There was a very recent paper that Pablo and Eunice, where they say like, well, okay, for reasonable assumptions, you probably need like only 7
No,
terms,
but that's
right?
in the metric. So they were looking at metric. They were looking at
Yeah.
the light ring, the ISCO, and all these things that you can
Yeah.
compute just from the metric.
Yeah.
But when you go down to quasi-normal modes, you're also numerical errors in integrating and so on. So the accuracy decrease. So in their paper,
So it doesn't follow through to
no.
to
In their, so if you do an icon, so if you trust iconal limit, then you can go from the metric and you have up to arbitrary speeds. But if you want to do the full computation, I think in their paper they give the expansion in the perturbations to higher order, but then when they quote the quasi-normal modes, they stop to second order. It's something. It's a work in progress. So it might be that this is gonna be improved very soon. But I think for the moment we don't get to 0.7 for sure. Yeah. Maybe 2.4.
So you're at the forefront of these ideas and looking at data. Don't we have a bias, a theorist's bias for looking at quasi-normal modes? I mean, after all, I think the lesson of what you're saying, this spectral instability, is that they're just not really good things to look at.
No, it's the opposite. So the point is that the spectrum is unstable, but the waveform is not.
Right, exactly. So you can just fit the waveform to your templates and extract the parameters that way. In principle, you don't need to do this decomposition into a quasi-normal modes. I think that's something we like because we can do it analytically and we're theorists and we like that, but you don't really need it. And it seems like the fact that the spectrum is unstable.
What do you mean you don't need, like, you know how to model the waveform because you know quasi-normal modes, right? So you know that.
No, you can just do the full waveform in numerical GR. You never need to talk about quasi-normal modes. That's like an extra complication.
But then you don't need to talk about the horizon. So I don't like this argument because this argument fails as soon as you look for, as soon as you want to include a different effects. Numerical relativity is not predictive outside the small range in which you can do simulation. So if I tell you now I'm going to search for a deviation in the horizon flux, you have no idea how to do it in numerical relativity. If I have an analytical understanding of the waveform, I can just change a well-controlled piece that I understand and go from there. And also numerical relativity, in principle, you have to include eccentricity, precession, and a bunch of different effects. And the point about instabilities is that if you do whatever you like to the potential, you will get instabilities. But my point with the loop quantum gravity metric was that there are physical, so it seems that physical deviations from the horizon, well-controlled and physically motivated, do not actually show spectral instabilities. It's just they're linearly epsilon. If you put a charge on the black hole, the spectrum doesn't go crazy. The spectrum changes linearly with the charge.
But I guess, okay, this is the crux of the problem. If I just have some heavy star near the black hole or just some strong object, some heavy object, isn't that going to deform the potential by introducing a bump? So generically, doesn't that mean that we just don't expect the real black hole in the sky to actually have the Kerr QNM spectrum?
Yeah. So it's a very good point. So when people refer to the final state conjecture, they refer to the thing that we don't only so the point is that these are not Kerr black holes, right? These are Kerr black holes immersed into the real universe with things around them. So the final state conjecture, which is more important than the Kerr conjecture, is the final state of these mergers going to a Kerr black hole. And so the point, and of course it depends on the kind of environment you're probing, right? So but you can show that, at least from what we expect, gravitational wave tests are clean, because whatever you put, dark matter, magnetic fields, even environments, at least in the LIGO-Virgo-Kagra band, you don't expect them to give observable deviations. For LISA, that's a problem. If you want to model extreme acceleration in spirals, you have to worry about dark matter models and accretion disk and all of this. But for these systems, you do not.
Well, there's some kind of contradiction, because you're saying that an epsilon change to the metric can produce some 1 over epsilon change to the spectrum, but somehow I shouldn't worry about that. So, yeah, but it is a problem for LISA. I mean,
no.
If as soon as you change the metric, the QNM spectrum is gone, that's a problem for any black hole spectroscopy. What am I missing?
No, it's not. So the problem is that the time domain signal retains memory of the unperturbed case, even if you have a perturbation. And that's what's going to matter. So the point is that the spectrum is not the right quantity to look at, because the spectrum doesn't have causality built in. What you want to look at is some quantity which also the observable has causality built in.
Okay, but now you are saying that the QNM spectrum is kind of the wrong thing to look at. You're saying we shouldn't look at the poles in the Green's function.
I'm saying that the QNM spectrum of the system retains memory of the unperturbed black hole. And also, the thing I showed you was a kind of an ad hoc perturbation. If I show you something else, it will not deform the spectrum. So I'm just saying that the claim that people have been doing, that whatever you do to the perturbation, the quasi-normal modes change completely, is simply not true. Because we can do numerical relativity simulations and we can extract quasi-normal modes. So that tells you that the waveforms that we look at have memory of the true spectrum in GR. It's just telling you that be careful of putting arbitrary modifications to the black hole potential, because you might get crazy answers, but in reality, you don't have crazy behavior.
Could I ask a follow-up question in a slightly different way? In fuzzballs and things like that, you completely change the quasi-normal mode spectrum, but does the waveform of mergers therefore look the same? In other words, you can't tell whether you could do radical change to the quasi-normal modes, and am I correctly taking away the message that it doesn't change the ring down very much?
The message is it depends. It depends in which class it falls into. And that's why you need to actually have simulations, as Daniel was saying, because if it falls in a certain classes of perturbation, then the spectrum is going to be fine. The waveform is going to reflect the spectrum. But in other cases, it might not. So so the point is that don't assume that just computing the spectrum, you will know immediately what the signal will look like. It might be completely different.
Okay, another way to say it is that it's not every epsilon size perturbation which leads to an instability of the spectrum. So there's some which are unstable,
yes,
and some which are not.
Yes.
One last quick question.
My statement is that can you actually formulate a theorem that one can go and study? I mean, so you're saying that there are some additional physical input to say when a spectrum can be stable or not.
Mm-hmm.
So is there a way to actually characterize what those physical input
that's
are?
my conjecture. So my conjecture is that by studying several, so in the literature and what we tried to do several things, and to me the take-home message for the moment, it seems that if you do physically motivated changes, then the spectrum seems to be stable. If you do something crazy like an oscillating perturbation which goes on forever, then you get something crazy. So, but there is not. So the latest work by Jaramillo et al. Put this in a very, very robust mathematical framework of non-self-adjoint operators, but there are no theorems that tells you how to distinguish this.
Okay, but this is then a property of the potential that you should derive in this background. It has to satisfy certain properties to be stable, which is a math problem, not a physically observed physics problem.
There's also the problem of the dynamics. So when you get the signal, then you don't only have the potential, you have the full dynamics built in. And so, but just to make a final point on this, in principle, if the spectrum is stable, when you simulate two black holes on a computer, you should get something completely different. We simulate black holes on a computer, and from those signals, we can extract the quasi-normal mode frequencies predicted by linear perturbation theory. So this tells you that even if in the computer, the potential is not going to be continuous, right? It's going to be step-like. And that is a perturbation to the potential. But in that case, we get sensible waveforms, and we extract actually the quasi-normal modes predicted by linear perturbation theory.